If I'm cycling along at a steady speed and changing direction, am I keeping a constant speed? Yes. But am I keeping a constant velocity? Well, no, because velocity, as you know, is a vector. Vectors have size and direction. And if the direction is changing, it doesn't matter about the speed. If the direction is changing, the velocity must be changing. And as you know, if there's a velocity change, there must be an acceleration. And that's what I want to look at today in terms of uniform circular motion. Last day, we had a look at definitions of circles, in particular focused on the radian. We ran through all this, and we saw that the radian was equal to the angle swept out by an arc where the length of the arc was equal to one radius. And this was more importantly, one circle was 2 pi radians. So 360 degrees is 2 pi radians. We also looked at how to set our calculators appropriately for this. What I want to look at today is the relationship between the speed of something that's going around in a circle and its acceleration. So uniform circular motion is what this topic is called. And when something is described as moving in uniform circular motion, it means that it's orbiting or going around in a circle at a steady speed. If you were driving in a car around a roundabout and the speedometer in the car read 20 miles an hour and you just kept on going round and round, that would be uniform circular motion. As well as moving at a constant speed, the radius of rotation is also constant. So the important thing to remember is that we're moving at a constant speed. Now, the speed may be constant, but don't forget that means that because the direction is changing, the velocity is not constant. We have a changing velocity. And because there's a velocity change, there must be an acceleration. Now, what you may know from GCSE already is that acceleration is what we call a centripetal acceleration. Because the speed is not changing, there can be no component of the acceleration in the same direction as that speed. If there was an acceleration in the same direction as the speed, you get an increase or decrease of speed. But because we're only getting a change in direction, it means that the acceleration must be at right angles to the direction of motion at all times. And that's what we call centripetal. It is always seeking the center. And because of Newton's second law, if there's an acceleration, there must also be an unbalanced force. So we end up with a centripetal force. Let's have a look at these things in more detail. So we've slowed it down a bit here. As this object is orbiting, it sweeps through an angle. We'll call that angle theta. So let's pause that there. And that's what we call having an angular velocity. So we saw that the radius that was moving swept round through an angle in a certain amount of time. And in the same way as speed is distance divided by time, angular velocity is the angle divided by the time. We give the symbol omega, which is this sort of curly W shape, to angular velocity. So omega equals theta over t, where theta is the angle swept out and t is the time taken. If we did that for one complete circle, what's the angle theta? Well, it's going to be 2 pi radians. And the time taken would be a capital T, the time period. So if we looked at this for one complete revolution, omega would be 2 pi over t. So 2 pi is the angle of a complete circle, and capital T is the time period, the time taken to move through that complete circle. So omega equals 2 pi over t. That's an important formula. That's one that you're going to see in this topic and in simple harmonic motion as well. Because frequency equals 1 over t, sometimes we write down omega as 2 pi f. We're less likely to use that in this topic, but it is one that you're going to have to use in the future. If we consider the speed of the object that's moving around, it has a linear velocity, which we'll call v. This is a bit confusing because, as we've already said, velocity is constantly changing, but we're going to assume that this is a constant velocity. It's really a speed. If you were driving a car, this would be the speed on the speedometer. Now, if we think how we can work this out, what's the relationship between v and omega? Think of one complete circle again. What's the distance around one complete circle? That's the circumference, which is 2 pi r, or pi d, 2 pi r, where r is the radius of the circle. The time it takes to complete one complete circumference is again going to be the time period, t. So if we did speed equals distance over time, the distance is 2 pi r, and the time is t, the time period, we can say that v equals 2 pi r over t. If we think back to our last slide, we saw that 2 pi over t was equal to omega, so we can substitute that in and say v equals r times omega. Again, that's a formula that's mentioned in the specification, and it links the radius of the circle, the speed at which an object is travelling, its linear velocity, or sometimes known as its tangential velocity, and the angular velocity, omega. We've said that because there's a change in direction, there must be an acceleration. And I've already mentioned that acceleration cannot be in the same direction as the direction of motion. If there was any component of acceleration in the same direction as the direction the object is travelling, that would cause the object to speed up or slow down. This is not the case in this case, so it means that all acceleration must be perpendicular to the direction of motion. Because the object is moving at a tangent to a circle, in other words at right angles to a radius, it means the acceleration must be along a radius towards the centre. And no matter what direction the object's moving, the acceleration will be at right angles to the speed or to the velocity and towards the centre of the circle. The formula for acceleration is omega squared r. We're not going to derive that, you don't need the derivation of that. It's also equal to v squared over r. So again, those are two formula that we're going to be using a fair amount. Make sure you know those. So a equals omega squared r, and a is equal to v squared over r. You can get the second by substituting v equals r omega into the first. Newton's second law tells us that any acceleration is the result of a resultant force. We know that Newton's second law says that the size of the acceleration is directly proportional to the resultant force and inversely proportional to the mass. And we summarise that down to F equals ma. And we can do the same thing here. So the centripetal force, in this case, is just going to equal F equals m omega squared r, or F equals mv squared over r. So that's just the mass of the object multiplied by the centripetal acceleration. So for a quick overview of the equations that we've covered today, we have omega equals theta over t, where omega is the angular velocity, theta is the angle through which an object is, the angle swept out, and t is the time taken. It's also equal to 2 pi over t, t being the time period and 2 pi being one complete circle, 360 degrees. And that can be rearranged to omega equals 2 pi f. We've also learned that v equals r omega, where v is the linear velocity or tangential velocity, r is the radius of the circle, and omega is the angular velocity. From that we can see that if two things are moving with the same angular velocity, the thing with a larger radius must be moving at a faster speed. So to think of running around a running track, you've got a bigger distance to go around the outside of a bend or a smaller distance to go around the inside of the bend. If you want to keep up with somebody on the inside of the bend and you're on the outside, you have to run faster because you're covering a bigger distance in the same amount of time. Then we saw that a equals omega squared r, or a equals v squared over r. And by multiplying both of those formulae by m, we can get the centripetal force. F equals m omega squared r, or F equals mv squared over r.